Tonight, we're going to travel to places that should not exist, places where the laws of physics bend until they nearly break, where temperatures drop so close to absolute zero that atoms forget how to move, where gravity becomes so violent that time itself slows down, stretches, and warps into something unrecognizable, where entire regions of space spanning hundreds of millions of light years contain almost nothing, not stars, not gas, not dust, just a silence so vast and so complete that the human mind cannot hold it without trembling a little. These places are real. They have been measured, photographed, and confirmed by some of the most sophisticated instruments ever built by human hands. And yet, no matter how many times you read the numbers, something in you refuses to believe them. Because the universe, it turns out, is far stranger than anything we were ever prepared for. By the end of tonight, you are going to understand exactly why the cosmos feels, at its outermost edges, less like a place governed by order and more like something dreamed by a mind we will never fully comprehend. You're going to sit inside the silence of the largest void ever discovered, a hollow in space so enormous that if our own galaxy were lost inside it, we would never have known other galaxies existed. You are going to stand at the threshold of a black hole, 66 billion times the mass of our Sun. You're going to look at the edge of the observable universe, the literal wall beyond which nothing, not even light, will ever reach us, and feel the strange, quiet terror of knowing that what lies beyond that edge may go on forever. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a version of the universe that most of us carry around in our minds without ever examining it too closely. It is orderly. It is governed by rules. Gravity pulls things together at a predictable rate. Stars burn for billions of years and then quietly fade. Space is vast, yes, almost incomprehensibly vast, but it is also, in some deep and reassuring way, knowable. We have equations for it. We have telescopes pointed at it. We have spacecraft drifting through it right now, sending signals back to Earth from distances that would have seemed like pure mythology to any previous generation of human beings. The universe in this version is enormous and ancient and beautiful, but it is not strange, not truly strange. Not strange in a way that makes you sit very still in the dark and wonder whether the rules you thought applied everywhere might, in certain places, stop applying entirely. That version of the universe is incomplete. The real universe, the one that exists beyond the comfortable middle distance where our telescopes have the easiest time looking beyond the familiar catalogue of planets and moons and nearby stars. The real universe is something considerably more unsettling. It contains places where temperature drops to within a fraction of a degree of the coldest possible temperature anything can ever reach. It contains objects so dense that a single teaspoon of their material would weigh more than all the mountains on Earth combined. It contains voids, genuine, almost total voids, stretching across distances so large that our entire observable universe could fit inside them and still have room to breathe. These places do not exist at the edge of speculation. They are not hypothetical. They have been measured, mapped, and confirmed by some of the most careful scientific minds of the last century. They are real. And that, if you sit with it for a moment, is perhaps the most disorienting fact of all. What we're going to do tonight is visit 10 of them. 10 places in the known universe that feel, in every honest sense of the word, impossible. Not impossible because science cannot explain them. Science can, at least partially, explain most of them. But impossible in the way that a photograph of an ocean looks impossible to someone who has only ever known desert. Impossible in the way that the number 1 trillion feels impossible when you try to count it out in your head. These are places where the universe reveals what it is truly capable of when it operates without the gentle constraints that make our small corner of the cosmos so livable, so navigable, so human-scaled. And visiting them, even in imagination, even lying here in the dark with your eyes closed, changes something in the way you understand where you are. Before we go anywhere, I want to give you a sense of the framework we are working inside. The observable universe, the portion of everything that exists from which light has had enough time to reach us since the Big Bang, spans roughly 93 billion light-years from one side to the other. A light-year is the distance light travels in a single year, moving at just under 300,000 kilometers per second. That means 1 light-year is approximately 9.5 trillion kilometers. 93 billion light-years, then, is a number so large it has no honest comparison in human experience, and yet, and this is important, the observable universe is almost certainly not all of the universe. It is simply all of the universe we can see. What lies beyond that horizon, beyond the wall where light can no longer reach us, may extend for vastly longer, perhaps infinitely longer. We do not know. We may never know. And that uncertainty, that permanent and irreducible not knowing, is the background hum that runs beneath everything we're going to explore tonight. The 10 places we're going to visit are scattered across this immensity. Some of them are relatively close in cosmic terms, which still means tens of thousands of light years. Some of them are near the very edge of what we can observe, so distant that the light reaching our telescopes left its source before our solar system even existed. Each place is extreme in a different way. Some are extreme in size, some in temperature, or in the almost total absence of temperature. Some in density, some in emptiness, some in the sheer violence of the energy they produce. One of them is not really a place at all, but a boundary, the final boundary, the point beyond which the universe becomes permanently, irreversibly invisible to everything inside it. Together, these 10 places form a kind of portrait of what the universe actually is, as opposed to what we might prefer it to be. I want to say something before we begin moving through them, something I think is worth holding on to as we go. The fact that these places are extreme, that they feel impossible, that they trigger something close to vertigo when you genuinely try to comprehend their scale or their violence or their emptiness, does not make the universe hostile. I know it can feel that way. When you learn that the void we're about to visit is so large that 300 million light-years of almost pure nothingness separate the galaxies on either side of it, the instinct is to feel small and vulnerable and somehow threatened. But I would invite you to try on a different feeling tonight. These extreme places are not threats. They are the universe being fully, completely, unself-consciously itself. They are what physics looks like when it has room to run. And the fact that you are here, that a collection of atoms arranged into a curious, wondering, vaguely anxious human being is lying in the dark thinking about supervoids and hyperluminous quasars and the edge of the observable cosmos, that fact is, in its own way, just as extreme, just as improbable, just as deserving of the word impossible. We will come back to that at the end. For now, let me take you somewhere very, very empty. Imagine standing in a field on a clear night and looking up at the sky. You can see thousands of stars. They are not evenly distributed. They cluster, they streak, they form patterns, but they are everywhere. Now imagine that you could somehow step back from that view, far enough back that individual stars disappeared, and what you were seeing instead were entire galaxies. Hundreds of them, thousands of them. At cosmological scales, galaxies are the basic unit of structure, the way that stars are the basic unit of the night sky as seen from Earth. And just like stars, galaxies are not distributed randomly across space. They form filaments, walls, and clusters, enormous threads of matter that stretch across hundreds of millions of light-years, forming a structure cosmologists call the cosmic web. Between those threads are empty regions, voids, and most of those voids are, by ordinary cosmic standards, unremarkable. A few tens of millions of light-years across, mostly empty, nothing particularly unusual about them. But then there is the Boötes void, and the Boötes void is not ordinary in any sense of that word. The year was 1981. Astronomer Robert Kirshner and his colleagues were conducting a survey of galaxies in a region of the sky near the constellation Boötes, a survey that was, by the standards of the time, fairly routine. What they found was not routine at all. In a region of space that, based on everything astronomers understood about large-scale cosmic structure, should have contained thousands of galaxies, they found almost none. Not a dramatic reduction, not a sparse scattering, almost none. The region they had stumbled onto was, to a degree that seemed to make no sense, empty. Subsequent surveys confirmed and expanded the picture. The Boötes void, as it came to be known, spans approximately 330 million light-years in diameter. That is not a typo. 330 million light-years. To put that in terms that might mean something to the part of your brain that processes physical reality. If the Milky Way were located at the centre of the Boötes void, we would not have discovered that other galaxies existed until the 1980s. The void is so large and so genuinely empty that for most of human history we would have looked out at the sky and seen essentially nothing but our own galaxy. We would have assumed we were alone. Not alone in the sense of no other intelligent life, alone in the sense of no other structure, no other light, just us and an ocean of dark. The Bhuta's Void contains, as far as we have been able to determine, approximately 60 galaxies. 60! In a region of space that, if it matched the average density of the observable universe, should contain something on the order of 2,000 galaxies. The emptiness is not subtle. It is not a matter of interpretation or measurement error. Something happened in this region of the universe, something in the earliest epochs of cosmic history, that resulted in matter evacuating this volume of space almost entirely. The leading explanation involves the physics of the early universe, the way that quantum fluctuations in the moments after the Big Bang seeded the large-scale structure we see today. Voids form, according to this model, because matter flows outward along gravitational gradients toward the denser regions, the filaments and walls, and away from the emptier ones. Over billions of years, this flow empties the voids further and densifies the filaments further in a kind of self-reinforcing separation. The Bhuta's Void, in this picture, is simply the most extreme example of a process that operates everywhere. The universe sorts itself, and the Bhuta's Void is the leftover space. But here is the thing most people do not realize. That explanation, while plausible and well supported by computer simulations of cosmic structure formation, does not fully account for the scale of what we are looking at. The Bhuta's Void is larger than most models comfortably predict. It sits at an awkward size, big enough to be statistically unusual, not quite big enough to be definitively impossible under standard cosmology, but occupying that uncomfortable middle ground where scientists say the word anomalous and mean it. Some researchers have pointed out that the void's diameter is large enough to challenge the cosmological principle, the foundational assumption that, at sufficiently large scales, the universe looks roughly the same in every direction. If voids this large are common, the universe may be less homogeneous than our standard models assume. And if that is true, some of the equations we use to describe the cosmos may need to be revised in ways that are difficult to predict. The Bhuta's Void is not just empty space. It is a question mark written in the absence of light. I want you to try to feel the scale of this for a moment, even knowing that the human brain is genuinely not built for it. Light travels at just under 300,000 kilometers per second. In a single second, it crosses a distance roughly equivalent to 7.5 times the circumference of the Earth. In 1 year, it travels approximately 9.5 trillion kilometers, and to cross the Bhuta's Void from one side to the other, light would need 330 million of those years. 330 million years ago on Earth, the dinosaurs had not yet evolved. The supercontinent Pangaea was still in the process of breaking apart. The Atlantic Ocean did not exist, and a beam of light that set out from one edge of the Bhuta's Void at that moment would, today, still have not reached the other side. It would still be travelling, through emptiness, through a silence so profound and so total that there is no sound, no light, no radio signal, no gravitational wave strong enough to notice. Just space, expanding, with almost nothing in it. There is something that I find deeply affecting about the Bhuta's Void, and I want to try to name it before we move on. When we talk about the universe being mostly empty, a fact that cosmologists mention so routinely it has almost lost its power to surprise, we're usually talking about the emptiness between stars or between galaxies, which is real and vast but somehow still feels populated when you zoom out far enough to see the filaments and clusters and walls. The Bhuta's Void removes even that comfort. It is a place where the cosmic web simply does not exist, where the architecture of the universe has a hole in it, and standing at its edge, metaphorically, in the way that we can stand anywhere in imagination, you are confronted with the fact that the universe did not have to be full. It did not have to be structured. It did not have to contain us, or anything like us. It could have been this: 330 million light-years of almost nothing, and then more of the same, forever. The fact that it is not, that it also contains stars and planets and oceans and people lying awake in the dark thinking about it, that may be the most astonishing thing of all. There is something at the center of our galaxy, something that has been there for as long as the Milky Way has existed, roughly 13 billion years, sitting at the gravitational heart of everything we belong to, pulling 250 billion stars into a slow, majestic rotation around it. For most of human history, we had no idea it was there. The centre of the galaxy is hidden behind an almost impenetrable curtain of gas and dust, invisible to ordinary optical telescopes, shrouded in the kind of cosmic obscurity that feels, in retrospect, almost deliberate. It was only in the latter half of the 20th century, as astronomers began observing the sky in radio waves and infrared light, wavelengths that can penetrate dust in ways that visible light cannot, that the truth at the centre of the Milky Way began to come into focus. And what they found there was not what anyone had hoped for. What they found was a supermassive black hole, a concentration of mass so extreme that it defies every intuition the human mind has developed over a lifetime of navigating a world where things have surfaces, where matter takes up space, where you can point to something and say, there it is, that is where it ends. Sagittarius A star, named for the constellation in whose direction it lies as seen from Earth, contains approximately 4 million times the mass of our Sun compressed into a region smaller than the distance between our planet and the Sun itself. 4 million solar masses. If you tried to count to 4 million, one number per second, it would take you 46 days without stopping to sleep. And yet all of that mass, all of that almost incomprehensible gravitational weight, is packed into a space you could, in principle, draw on a map of the inner solar system. The Sun could fit inside it. The Earth could orbit inside it. The boundary of Sagittarius A star, its event horizon, sits at a radius of roughly 12 million kilometers from the singularity at its core. That is vast by human standards. By the standards of what is contained inside it, it is impossibly, terrifyingly small. The stars near the center of the galaxy know it is there. They cannot ignore it. In the 1990s and 2000s, two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany, and one led by Andrea Ghez at the University of California, Los Angeles, spent decades tracking the motion of stars in the innermost region of the Milky Way. What they observed changed our understanding of what black holes are and how massive they can become. One star, designated as 2, was found to orbit Sagittarius A star on a path that brings it within a distance of only about 17 light hours from the event horizon. That is closer to the black hole than the outer planets of our solar system are to our Sun, and it completes that orbit in just 16 years. 16 years. At its closest approach, S2 moves at a speed of approximately 7,600 kilometers per second. That is roughly 2.5% of the speed of the light. It is the fastest confirmed orbital motion of a star ever measured, and the gravity pulling it through that arc, bending its path through space with that degree of violence, comes from an object that, in the vacuum of the surrounding region, is invisible. In April of 2017, a global network of radio telescopes called the Event Horizon Telescope turned its attention to Sagittarius A star. The array used a technique called very long baseline interferometry, effectively combining telescopes spread across multiple continents to simulate a single dish the size of the Earth itself. The goal was to image the shadow of the black hole, the dark silhouette cast by its event horizon against the glowing material swirling around it. The result, released in May of 2022, after years of extraordinarily complex data processing, was the first direct image of Sagittarius A star. A blurry but unmistakable ring of orange and gold light, with a dark center, the shadow of 4 million solar masses of compressed space-time. It is one of the most remarkable photographs ever produced by human science. And one of the strangest things about it when you hold it in your mind is how close it is. Sagittarius A star is approximately 26,000 light-years from Earth. In cosmic terms, it is our neighbour. It is the black hole in our own backyard. Now, I want to take you closer. Not physically. Nothing about approaching a black hole is safe or survivable, and I want to be honest about that, but conceptually. Imagine you are in a spacecraft at a very safe distance from Sagittarius A star, far enough that its gravity feels no stronger than the gravity of a particularly massive star. From there, looking inward, you would see a ring of superheated gas and plasma, the accretion disk, glowing at temperatures of millions of degrees, churning and spiraling inward with an energy that produces more light than billions of ordinary stars combined. Behind that ring, space itself would appear to curve. Light from stars behind the black hole would be bent around it, creating strange arcs and halos, a gravitational lensing effect that distorts the background sky into shapes no optical illusion on Earth could replicate. And at the centre, darker than anything you have ever seen, the event horizon itself, the point of no return, the boundary beyond which nothing, not matter, not light, not information of any kind, can ever escape. It does not look like a surface. It looks like an absence, like a hole cut in the fabric of the visible universe. Sagittarius A star is currently in a relatively quiet phase. Astronomers describe it as dormant, not actively consuming large amounts of material, not producing the brilliant jets of energy that active galactic nuclei in other galaxies emit. But it has not always been quiet. Evidence preserved in the structure of gas clouds near the galactic centre suggests that a few million years ago, Sagittarius A star experienced an episode of violent activity, a feeding event that lit up the galactic core with radiation powerful enough to have been visible across the local group of galaxies. Something fed it, something large fell in, and the result was a flare of energy that would have outshone the entire galaxy at certain wavelengths. That outburst has long since faded. The monster, for now, sleeps. But it is there, 26,000 light-years away, patient in the way that only something eternal and gravitationally inevitable can be patient, pulling 250 billion stars in their slow and ancient dance around it, including our sun, including our solar system, including you. We need to talk about size, not the ordinary kind of size, not the size of mountains or oceans or continents, not even the size of planets or the distances between them. We need to talk about a kind of size that the human brain was simply never designed to process, a scale so far outside the range of anything our ancestors ever needed to measure or navigate, that engaging with it honestly requires a deliberate act of imagination. We are going to try that act together, right now. And the object we are going to use as our guide is a star called Stephenson 218, a hypergiant sitting in the constellation Scutum, approximately 19,000 light-years from Earth, that holds the current record as the largest known star in the observable universe by radius. I want you to hear that clearly. Of all the stars that have been observed and measured across the entire observable universe, across 93 billion light-years of space containing an estimated 2 trillion galaxies, each containing hundreds of billions of stars, Stephenson 218 is the largest one we have found. And what that means, in concrete physical terms, is something that I think will stay with you. Let us start with something familiar. Our Sun is, by any reasonable human standard, enormous. Its diameter is approximately 1.4 million kilometers. You could line up 109 Earths side by side across its face. Its volume is so large that approximately 1,300,000 Earths could fit inside it with room to spare. The Sun contains 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of interplanetary dust, all of it together amounts to less than 0.25% of what the Sun contains. It is, in every practical sense, the solar system. Everything else is footnotes. And yet, as stars go, our Sun is not particularly impressive. It is a yellow dwarf, a middling, average, unremarkable star by the standards of the galaxy. There are stars out there that make our Sun look like a candle flame standing next to a bonfire. Stephenson 218 is not even a bonfire. Stephenson 218 is a wildfire visible from space. The radius of Stephenson 218 is approximately 2,150 times the radius of our Sun. Let that number sit for a moment before we go further. 2,150 times. If you replaced our Sun with Stephenson 218, if you place this star at the centre of our solar system, right where the Sun sits now, its surface would not stop at the Sun's current boundary. It would not stop at Mercury. It would not stop at Venus or Earth or Mars. It would engulf all 4 inner planets without slowing down. It would expand outward through the asteroid belt. It would swallow Jupiter. It would consume Saturn. And its surface, the visible outer edge of this single star, would extend to approximately the orbit of Saturn, roughly 1.4 billion kilometers from where the centre of our solar system currently sits. Earth would not orbit this star. Earth would be inside it. You and everything you have ever known would exist within the outer layers of a single stellar atmosphere. That is not a metaphor or an exaggeration. That is the geometry. Now let us talk about what Stephenson 218 actually is, and why stars of this scale exist at all. Stephenson 218 is classified as a red hypergiant, the largest category of star by physical size, and one of the rarest. It is a member of a stellar cluster called Stephenson 2, embedded in a dense region of the Milky Way rich in massive stars. Its surface temperature is relatively cool for a star, approximately 3,200 degrees Kelvin, compared to our Sun's approximately 5,778 degrees Kelvin, which is precisely why it is so physically large. The outer layers of the star have expanded and cooled dramatically, puffing outward to their extraordinary radius while the core continues to burn. This expansion is not stable in any long-term sense. Red hypergiants are stars in the late stages of their lives, burning through their fuel at rates that would be unsustainable over billions of years. Stephenson 218 is, in cosmic terms, near the end of its story. It is a star in its final act, swollen and luminous and temporary in the way that all the most spectacular things tend to be. The luminosity of Stephenson 218 is another number that requires a moment of honest processing. It shines with a brightness estimated at approximately 400,000 to 600,000 times the luminosity of our Sun. That means it releases, every single second, the equivalent of between 400,000 and 600,000 times the energy our Sun releases in that same second. Our Sun already releases approximately 3.8 times 10 to the power of 26 watts of power continuously, a number so large it has no meaningful human analogy. Multiply that by 500,000 and you begin to approach the energy output of Stephenson 218. This is why, despite being 19,000 light-years away, it is detectable at all. Stars of ordinary size at that distance would be invisible to the naked eye. Stephenson 218 burns bright enough to be catalogued from across a significant fraction of the galaxy's width. It is not hiding, nothing that luminous could hide even if it wanted to. Here is the thing most people do not realize about stars at this scale. Physics itself imposes a limit on how large a star can grow. The reason that limit exists is a phenomenon called radiation pressure, the outward push that a star's own light exerts on its outer layers. As a star grows more massive, it burns hotter and brighter, and the radiation pressure from its core pushes outward against gravity with increasing force. At a certain threshold, somewhere in the range of 150 to 300 solar masses, depending on conditions, the radiation pressure becomes so strong that the star begins to blow itself apart. It sheds mass through powerful stellar winds. It pulsates, contracts, and re-expands in cycles. It is perpetually at war with its own output, hovering at the edge of coherence. Stephenson 218, with its extraordinary radius, represents a configuration that exists right at the boundary of what stellar physics permits. It is not supposed to be this big, and yet here it is. 2,150 solar radii of swollen luminous temporary enormity, sitting in the galaxy like a reminder that the universe does not always ask permission before doing something that should not be possible. There is a map of the oldest light in the universe. It was created not by a single telescope, but by a series of space observatories. First COBE in the early 1990s, then WMAP in the 2000s, then the Planck satellite through the 2010s. Each one more sensitive than the last, each one peering deeper into the faint afterglow of the Big Bang with greater precision. That afterglow is called the cosmic microwave background radiation, and it is one of the most important objects of study in all of cosmology. It is the light released approximately 380,000 years after the Big Bang, when the universe had cooled just enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing light to travel freely through space rather than being constantly scattered by a fog of charged particles. That ancient light fills the entire sky. It comes from every direction simultaneously, and it carries within it, encoded in tiny variations of temperature, a detailed record of the state of the early universe. The seeds of every galaxy, every filament, every void that would eventually grow into the cosmic web we live inside today. When you look at this map, you're looking at a baby photograph of everything that exists. The map is almost perfectly smooth. The temperature of the cosmic microwave background is approximately 2.7 degrees Kelvin, just 2.7 degrees above absolute zero, and across the entire sky, that temperature varies by only tiny fractions of a degree. Those tiny variations are not random noise. They are the imprints of quantum fluctuations in the earliest moments of the universe, stretched to cosmic scales by a period of rapid expansion called inflation, and they correspond with extraordinary precision to the large-scale structure we observe today. Cosmologists can look at a hotspot in the microwave background map and trace its gravitational legacy forward through 13.8 billion years to a cluster of galaxies visible in our current sky. The map is not just a photograph, it is a Rosetta Stone. A key to understanding how the universe went from a nearly featureless hot plasma to the complex structured inhabited cosmos we find ourselves in. Which is why, when something in the map does not fit, it matters enormously. And there is something in the map that does not fit. In the southern sky, in a region corresponding to the constellation Eridanus, there is an area of the cosmic microwave background that is measurably colder than its surroundings. Not by a dramatic amount. The temperature difference is only about 70 microkelvins, which is 70 millionths of a degree, but in a map where the total variation across the entire sky amounts to only about 200 microkelvins from the coldest to the hottest point, a single region accounting for 70 microkelvins of that difference is a profound statistical anomaly. This region spans approximately 5 degrees across the sky, roughly 10 times the apparent diameter of the full moon as seen from Earth, and it has been confirmed by multiple independent analyses using data from multiple independent satellites. It is real. It is not an artifact of measurement. It is not a calibration error. It is genuinely there, and it genuinely should not be. Cosmologists call it the CMB cold spot, and it is one of the most argued about features in modern astronomy. The most straightforward explanation for the cold spot involves something called a supervoid, an enormous region of space, roughly 1 to 3 billion light-years in diameter, containing significantly less matter than average, positioned between us and the surface of last scattering. When light from the cosmic microwave background travels through a void, it can lose a small amount of energy, a phenomenon called the integrated Sachs-Wolf effect, which would cause that region of the map to appear slightly colder. Surveys of the galaxy distribution in the direction of the cold spot have found some evidence of an underdensity in that region, a hint of a supervoid, though the evidence is not conclusive, and the scale of the temperature anomaly appears larger than the supervoid alone can fully account for. The numbers, as physicists say with polite but meaningful emphasis, do not quite work out. The supervoid is real, or at least probably real, but it is probably not the whole story. And that gap between the explanation and the anomaly is where things become genuinely interesting. Because there is another explanation, one that is considerably more dramatic, considerably more difficult to test, and considerably more unsettling in its implications. Some cosmologists have proposed that the CMB cold spot is the imprint of a collision between our universe and another universe, a separate bubble of space-time that briefly made contact with our own in the earliest moments of cosmic history and left a bruise on the fabric of the early universe. This idea emerges from a theoretical framework called eternal inflation, in which the period of rapid expansion that followed the Big Bang produced not one universe, but an effectively infinite number of them, a multiverse of separate bubbles, each with its own physical laws, each expanding independently, occasionally colliding at their boundaries. If our universe collided with a neighbouring bubble before or during the period when the cosmic microwave background was formed, the resulting disturbance could, under certain theoretical models, produce exactly the kind of cold, anomalous region we observe. Not definitely, not provably, but possibly, and possibly is a word that, when spoken in the context of a collision between universes, carries an enormous amount of weight. I want to sit with that for a moment before we move on, because I think it deserves more than a passing mention. The cold spot, if the collision hypothesis is correct, would be direct observational evidence that our universe is not the only one. It would mean that the map of the oldest light in the sky contains, in one small cold patch slightly below the celestial equator, the fingerprint of contact with something that exists entirely outside our universe, something that operates, perhaps, under different physical laws, with different constants, a different history, possibly no stars, no matter as we understand it, no time flowing in a direction we would recognize. The idea is speculative. The evidence is ambiguous. Most cosmologists are cautious about it for very good reasons. But the cold spot is real, the anomaly is confirmed, and the standard explanation does not fully account for it. That means the question remains open, and an open question of that magnitude, sitting quietly in the oldest light in the universe, 5 degrees wide in the southern sky, just slightly colder than everything around it, is one of the most extraordinary things I know of. There are things in the universe that produce light. Stars produce light through nuclear fusion, the same process that warms your face on a summer afternoon, scaled up to a degree that our sun releases energy equivalent to the detonation of roughly 91 billion megatons of TNT every single second. Galaxies produce light because they contain hundreds of billions of stars doing exactly that, all at once, their combined output creating the faint smudges we see in long exposure photographs of the deep sky. These are the light sources we tend to think of when we think about a luminous universe: stars and galaxies, fire and fusion, the gentle arithmetic of hydrogen becoming helium, becoming energy, becoming light. And then there are quasars. Quasars are not gentle. Quasars are not arithmetic. Quasars are what happens when the universe decides to produce light in quantities that make galaxies look like street lamps, powered by a mechanism so violent and so total that describing it accurately requires language that keeps sliding toward the apocalyptic. And of all the quasars ever catalogued across the observable universe, one stands above the rest in a way that I find genuinely difficult to communicate without simply repeating the numbers until they land. TON 618. The name is not poetic. It comes from the Tonantzintler Catalogue, a mid-20th century survey of blue stellar objects conducted at the Tonantzintler Observatory in Mexico. It was initially classified as an unusually blue star, which is the kind of understatement that makes astronomers wince in retrospect. TON 618 is not a star. It is a quasar, a quasi-stellar object, located approximately 10.4 billion light-years from Earth in the direction of the constellation Canes Venatici. The light reaching our telescopes from TON 618 left its source when the universe was only about 3.3 billion years old. Our solar system did not yet exist. The atoms that would eventually form Earth, form the oceans, form the first living cells, form every organism that would ever live and die on this planet. Those atoms were still scattered across the interstellar medium of a young and violent cosmos, not yet gathered, not yet ignited. And from that remote era, TON 618 has been sending light across the expanding universe ever since. Light that carries within it a record of energies so extreme, they test the descriptive capacity of human language. At the heart of TON 618 is a black hole. This is true of all quasars. They are powered by supermassive black holes actively consuming enormous quantities of surrounding material, a process that releases energy with an efficiency far greater than any other mechanism in the known universe. But the black hole at the centre of TON 618 is not merely supermassive, it is ultramassive, a word astronomers coined specifically because supermassive was no longer adequate. Its mass is estimated at approximately 66 billion times the mass of our Sun. 66 billion solar masses. To place that in context, the black hole at the centre of our own Milky Way, Sagittarius A star, contains approximately 4 million solar masses, and we have already established how staggering that number is. TON 618's central black hole is roughly 16,500 times more massive than Sagittarius A star. Its event horizon, the sphere of no return, the boundary beyond which nothing escapes, has a radius of approximately 197 billion kilometers. That is larger than the distance from our Sun to the nearest star system, Alpha Centauri. A single black hole whose event horizon alone spans a volume larger than the space between neighbouring star systems. It is the largest confirmed black hole ever measured. The luminosity of TON 618 is where the numbers become almost liturgical in their excess. This quasar shines with a brightness approximately 670 trillion times greater than our Sun. 670 trillion. The entire Milky Way galaxy, with its 250 billion stars burning simultaneously, produces a combined luminosity of roughly 20 to 40 billion times that of our Sun. TON 618 outshines the entire Milky Way by a factor of roughly 30,000. If you replaced our galaxy with TON 618, if you placed this single quasar where the Milky Way now sits, the night sky as seen from Earth would not be dark. It would be a wall of light. The energy output of this object, arriving from 10.4 billion light-years away, is still bright enough that a moderately sized telescope on Earth can detect it. That is how luminous TON 618 is. Across 10 billion light-years of expanding space, it is still visible, still shouting. The mechanism producing this light is, in its own way, as strange as the numbers themselves. When a supermassive black hole actively consumes surrounding material, that material does not fall straight in. Angular momentum causes it to spiral inward, forming a flattened rotating structure called an accretion disk, a vast whirlpool of gas and plasma thousands of times larger than the event horizon itself. As material in the accretion disk spirals inward, it compresses and heats through friction and magnetic forces to temperatures of millions, sometimes tens of millions of degrees. At these temperatures, the disk radiates across the entire electromagnetic spectrum, from radio waves to visible light to X-rays to gamma rays. The innermost regions of the accretion disk, closest to the event horizon, move at significant fractions of the speed of light. The magnetic fields threading through this environment are so intense, they can redirect some of the infalling material into twin jets of plasma that shoot outward along the black hole's rotational axis at velocities approaching the speed of light, extending for distances that can exceed the diameter of the host galaxy itself. This is a quasar. This is the engine behind TON 618, a 66 billion solar mass black hole surrounded by a disk of plasma heated to millions of degrees, consuming material at a rate of hundreds of solar masses per year, and releasing the resulting energy as light that can be seen from the opposite side of the observable universe. I want to leave you with one image before we move on. Imagine you are in a spacecraft positioned at a distance of, say, 1 light-year from TON 618, close enough for the geometry of the thing to be visible, far enough that you have not yet crossed any boundary from which return is impossible. What you would see, filling a significant portion of your field of view, would not be a star or a galaxy in any recognizable sense. The accretion disk alone would span a region hundreds of billions of kilometers across, glowing with a blue-white incandescence brighter than anything the human eye evolved to process. The event horizon at the center would appear as an absolute darkness, not the darkness of a night sky with stars removed, but a genuine, total, physical absence of light, a sphere of nothing against a background of everything. The jets extending above and below the disk would stretch beyond your visible horizon, rivers of accelerated plasma moving at fractions of the speed of light, generating their own radiation as they go. There would be no sound. There is never sound in space. But if there were, I imagine it would be something below the threshold of hearing, a vibration felt more than heard, the way a large enough explosion does not arrive as a sound but as a pressure. TON 618 does not make noise. It makes the universe tremble at a frequency we were never built to hear. Time feels like the most reliable thing there is. It moves forward. It moves at a steady rate. 1 second here is 1 second there. 1 hour in your bedroom is 1 hour on the other side of the planet, 1 hour on the moon, 1 hour anywhere in the universe you care to name. This is not just an intuition. It is the deepest assumption embedded in the way human beings experience reality. We build our lives around it. We synchronize our clocks, coordinate our schedules, measure our lifespans in years that we trust are the same length, regardless of where we happen to be standing. Time, of all the features of physical reality, seems like the one thing that cannot be negotiated with, cannot be distorted, cannot be made to behave differently depending on circumstance. And yet, this assumption, this foundational certainty that time is universal and constant, is wrong. It has been wrong since 1905, when a 26-year-old patent clerk in Bern named Albert Einstein published a paper that rewrote the relationship between space, time, motion, and gravity. We have known for more than a century that time is not fixed, but knowing it intellectually and feeling it, really feeling the vertigo of what it means, are very different things. And there is a place in the universe, a dead star spinning at an almost incomprehensible rate, approximately 550 light-years from Earth, where the distortion of time is not theoretical. It has been measured. It has been confirmed. And the number that came back is one of the most quietly terrifying facts in modern physics. The object is called PSR J0437-4715. It is a millisecond pulsar, a type of neutron star which is itself a type of object worth pausing on before we go further. When a massive star exhausts its nuclear fuel and collapses, the result depends on how massive the star was. If the core that remains after the collapse falls within a certain mass range, roughly between 1.4 and 3 solar masses, it does not collapse all the way to a black hole. Instead, it stops at a state of matter so dense it has no analogue anywhere in ordinary experience. In a neutron star, the electrons and protons of ordinary atoms have been crushed together by gravitational pressure so extreme that they merge into neutrons, packed together at densities approaching those found inside atomic nuclei. A neutron star containing 1.5 times the mass of our Sun occupies a sphere roughly 20 kilometers in diameter, a sphere you could drive across in about 12 minutes at highway speeds. Its density is so extreme that a single teaspoon of neutron star material, scooped out and transported to Earth, would weigh approximately 10 million metric tons. That is roughly the mass of a mountain, compressed into a volume smaller than a sugar cube. This is what PSR J0437-4715 is made of, and it is spinning. It is spinning at 174 rotations per second. 174 full rotations complete 360-degree turns every single second. To put that in terms your body can almost relate to, a standard ceiling fan on its higher setting rotates at roughly 3 rotations per second. A dentist's drill, one of the fastest rotating objects most people ever encounter, spins at hundreds of rotations per second in its fastest configurations. PSR J0437-4715 spins faster than many dental drills, and it does so as an object with a mass 1.5 times that of our Sun and a diameter of 20 kilometers. The centrifugal forces at the equator of this star are extraordinary. The magnetic field it generates is billions of times stronger than the strongest magnetic fields ever produced in a laboratory on Earth, and as it spins, its magnetic poles sweep through space like lighthouse beams, emitting pulses of radio waves with a regularity so precise that millisecond pulses are sometimes described as the most accurate natural clocks in the universe, more stable, over long timescales, than the atomic clocks we use to define the second here on Earth. In 2024, a team of astronomers published results of a years-long observational campaign targeting PSR J0437-4715 using the Meerkat Radio Telescope Array in South Africa. What they were measuring was the effect of the pulsar's gravitational field on the rate at which time passes in its vicinity, a direct test of one of the predictions of Einstein's general theory of relativity. General relativity tells us that gravity is not simply a force between masses. It is a curvature of space-time itself, a warping of the fabric in which space and time are woven together. And one of the consequences of that warping is gravitational time dilation. The stronger the gravitational field, the slower time passes, relative to a distant observer in weaker gravity. We already knew this was real. GPS satellites have to correct for gravitational time dilation constantly. The clocks on those satellites run slightly faster than clocks on Earth's surface because they sit higher in Earth's gravitational field. The effect is tiny but measurable and mission critical. Without the correction, GPS positioning would drift by kilometers per day. The physics is not in dispute. What the 2024 measurement did was test it in a gravitational environment incomparably more extreme than anything achievable on or near Earth, with a precision that surpassed all previous measurements of its kind. The results confirmed general relativity's predictions with extraordinary accuracy. Time on the surface of PSR J0437-4715 runs measurably, significantly slower than time at a safe distance from it. The gravitational field of this neutron star is so intense that the dilation effect is not a subtle correction requiring atomic clocks to detect. It is a substantial, physically real difference in the rate at which time itself elapses. If you could somehow hover just above the surface of this pulsar, an impossibility in practice but a useful thought experiment, and watch a clock positioned at a safe distance from the star, you would see that distant clock running fast. Not because it is malfunctioning, because time out there is genuinely moving faster than time where you are. The gravity of the pulsar is not just pulling you toward its surface, it is pulling time itself, slowing it, bending it, making the universe's most fundamental constant into something local and variable and dependent on where you happen to be standing. This is the thing I want you to hold tonight as you drift towards sleep. not the equations, not the measurement precision, not the technical vocabulary of general relativity. Just this: time is not the same everywhere. The universe does not run on a single clock. Every massive object in the cosmos, every planet, every star, every neutron star and black hole, creates a little pocket of slower time around itself, a dimple in the flow of moments where the universe ages more slowly than it does in the open spaces between things. You're sitting in one of those pockets right now, on the surface of a planet massive enough to make your clock run slightly slower than it would if you were floating in interstellar space. The effect near Earth is too small to feel, but it is there. The same physics that makes GPS satellites need correction, the same physics confirmed in 2024 by measuring a spinning dead star 550 light-years away, is operating on you, right now, in this moment. Time is bending around you. It has always been bending around you. The universe just waited until the 20th century to tell us. We have been spending time with objects of almost unthinkable enormity. A void 330 million light-years across. A black hole 66 billion times the mass of our Sun. A star whose surface would swallow Saturn's orbit. The universe, as we've been exploring it tonight, tends toward the grandiose, the excessive, the scale that defeats comprehension on the first pass and leaves you reaching for analogies that ultimately fail. But the universe is not only large, it is also, in ways that are equally strange and equally difficult to internalize, small. It operates at extremes in both directions simultaneously, and some of the most improbable things it has produced are not the most enormous, but the most marginal, objects that exist right at the boundary between one category of thing and another, teetering on the knife edge of a physical threshold, sustained in their existence by conditions so precisely balanced that a modest change in any direction would result in something fundamentally different. Tonight, we are going to visit one of those objects, a star, a genuine, hydrogen-fusing, light-producing star, one that is barely larger than the planet Saturn. The object is designated EBLM J0555-57 AB. It was discovered in 2017 by a team of astronomers from the University of Cambridge, using data from the WASP Exoplanet Survey, a program originally designed to detect planets transiting in front of distant stars, which occasionally turns up things considerably more surprising than planets. EBLM J0555-57 AB is part of a triple star system, orbiting a larger parent star at a distance that places it in the category of a stellar companion rather than a planet. It was detected because it periodically passes in front of its parent star as seen from Earth, causing a measurable dip in that star's brightness. The same technique used to find exoplanets, applied here to something that turned out to be a star in its own right. When the team calculated its size from the transit data and confirmed its mass through radial velocity measurements, the result was striking enough that it generated significant attention in the astronomical community. EBLM J0555-57 AB has a radius approximately 84% that of Saturn. It is, to within current measurement uncertainties, one of the smallest hydrogen-fusing stars ever confirmed. Let that settle for a moment. Saturn is a planet, a gas giant certainly, the second largest planet in our solar system, with a radius approximately 9.5 times that of Earth, but a planet nonetheless, a world without a solid surface, composed primarily of hydrogen and helium, famous for its rings and its moons and its extraordinary beauty in a telescope eyepiece. It is not, by any stretch of the definition, a star. It does not produce energy through nuclear fusion. It does not shine by its own light, and yet EBLM J0555-57 AB, which is physically smaller than Saturn, does. Somewhere inside that compact Saturn-sized sphere, temperatures and pressures reach the threshold required to initiate hydrogen fusion, the process of forcing hydrogen nuclei together to form helium, releasing energy in the process. The core of this star at its centre reaches temperatures of roughly 8 million degrees Kelvin, significantly cooler than our Sun's core temperature of approximately 15 million degrees, but still hot enough, barely, to sustain the reactions that define a star. This object is a star by the slimmest possible physical margin. The reason this margin exists, the reason there is a minimum size for a star at all, comes down to the physics of nuclear fusion and the conditions required to initiate it. At the centre of any object large enough to generate significant gravitational pressure, hydrogen is compressed and heated by the weight of all the material above it. For most objects, this compression produces heat and pressure, but never enough to push hydrogen nuclei close enough together to overcome their mutual electromagnetic repulsion and fuse. Jupiter, the largest planet in our solar system with a mass roughly 318 times that of Earth, gets partway there. Its core is hot and compressed, and it radiates more energy than it receives from the Sun, but it falls short of the fusion threshold by a significant margin. Objects between roughly 13 and approximately 80 times the mass of Jupiter, called brown dwarfs, can fuse a lighter isotope of hydrogen called deuterium, but cannot sustain the full proton-proton chain reaction that powers true stars. Only above roughly 80 Jupiter masses does the gravitational compression become intense enough to ignite genuine, sustained hydrogen fusion and cross the boundary from failed star to true star. EBLM J0555-57ab sits just barely above that boundary. It has precisely enough mass to be a star, and not 1 gram more than necessary. What would it look like, this minimum star? If you could approach EBLM J0555-57ab and see it with your own eyes at close range, it would not resemble our Sun. Our Sun is a brilliant white-yellow disk, far too bright to look at directly, radiating light across the full visible spectrum with an intensity that warms planets at distances of hundreds of millions of kilometers. This star would be dim by comparison, a deep, dark red, glowing with the color of cooling embers rather than the blaze of a fire at full strength. Its surface temperature is estimated at approximately 2,700 degrees Kelvin, making it what astronomers classify as an M-type red dwarf star, the coolest and smallest category of true star, at the very bottom end of even that modest range. In visible light it would be difficult to see. Much of its energy output falls in the infrared, light that human eyes cannot detect. You would feel its warmth before you saw its glow. It would look less like a star and more like a planet with a fever, a world that has just barely crossed the threshold into stellar existence, and maintains that status with the cosmic equivalent of a white-knuckled grip. There is something I find deeply moving about EBLM J0555-57ab, and I want to try to name it before we move on to our next impossible place. We tend to think of extremes as the things that dwarf us, the supermassive black holes, the hypergiant stars, the voids that swallow the imagination whole. But there is an extreme in the other direction that is, in its own quiet way, just as profound. The minimum, the threshold, the thing that barely qualifies. EBLM J0555-57ab is a star because the universe permits stars of this size, because the laws of physics draw the line precisely here, at this mass, at this temperature, at this radius, and not 1 step smaller. Below this threshold, objects cool and dim and become something other than stars. Above it, they ignite and burn and shine. This small, dim, Saturn-sized point of nuclear fire is the universe's answer to the question of how little it takes to make a sun. And the answer, it turns out, is not very much at all. There is something pulling us, not metaphorically. Not in the sense of gravitational attraction between nearby objects. The moon pulling the tides, the sun holding the planets in their orbits, the Milky Way and Andromeda slowly falling toward each other across 2.5 million light-years of intergalactic space. Something else, something larger. Right now, at this moment, as you lie still in the dark, the Milky Way galaxy, all of it, all 250 billion stars, all the gas and dust and dark matter and the 4 million solar mass black hole at its center, and our sun embedded within it, and the Earth orbiting our sun, and you lying on the surface of the Earth, all of it is moving through space at approximately 2.2 million kilometers per hour in a direction that took astronomers decades to identify, because for a long time the thing pulling us was hidden not by distance alone, but by our own galaxy. There is a region of the sky that astronomers call the zone of avoidance, the band along which the dense disk of the Milky Way lies, thick with gas and dust that blocks optical telescopes as effectively as a wall, and directly behind that wall, precisely in the region we could not easily see, something enormous was waiting to be found. Astronomers call it the Great Attractor, and understanding what it is and what lies beyond it requires first sitting with the scale of what we are actually talking about. The story of the Great Attractor begins in the 1970s and 1980s, when astronomers studying the peculiar velocities of galaxies, the component of a galaxy's motion that cannot be explained by the general expansion of the universe, began to notice a systematic pattern. Galaxies across a vast region of space, spanning hundreds of millions of light years in every direction, were all moving toward a common point in the sky. Not randomly. Not in the chaotic way you might expect if local gravitational influences were the only factor. Systematically, coherently, as if something of extraordinary mass were exerting a gravitational pull across an almost incomprehensible volume of space. The Milky Way was part of this flow. The local group, our galaxy, Andromeda, and the dozens of smaller galaxies gravitationally bound to them, was part of this flow. The Virgo cluster, the largest concentration of galaxies in our immediate cosmic neighbourhood, was part of this flow. Everything within a region roughly 500 million light-years across appeared to be drifting in the same direction, toward the same point, at velocities that implied a mass concentration far beyond anything visible in that region of the sky. Something was there. Something massive enough to pull hundreds of thousands of galaxies across hundreds of millions of light-years, and nobody could see it. The difficulty was the zone of avoidance. The plane of the Milky Way, dense with interstellar gas and dust, absorbs and scatters visible light so completely that optical telescopes are essentially blind to it. The Great Attractor sits almost precisely behind this obscuring curtain in the direction of the constellation Centaurus. As radio astronomy and X-ray astronomy matured, techniques that can pierce the dust that defeats optical observation, a clearer picture began to emerge. Within the region toward which everything is falling lies an enormous supercluster of galaxies called the Norma Cluster, also known as Abell 3627, a dense collection of galaxies approximately 220 million light-years away. For a time, astronomers believed the Norma Cluster itself was the Great Attractor, the mass concentration responsible for the observed gravitational flow, but as measurements improved, it became clear that the Norma Cluster, massive as it is, was not nearly massive enough to account for the full scale of the motion being observed. There was something more, something behind the Great Attractor itself. In 2014, a team led by astronomer Brent Tully published a landmark paper redefining the supercluster structure of the local universe. Using a sophisticated mapping of galaxy peculiar velocities, essentially tracing the gravitational flow lines of cosmic matter the way a hydrologist traces water flow to find watersheds. The team identified a previously unrecognized supercluster of galaxies spanning approximately 500 million light-years and containing the mass of roughly 100 million billion suns. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. The Milky Way sits near the outer edge of Laniakea, the Great Attractor region, the Norma Cluster, the dense filaments and walls of the inner supercluster. All of these lie toward the center of Laniakea, a center toward which the entire supercluster's galaxy population is slowly, inexorably flowing. We are not just being pulled toward something, we are falling toward the gravitational heart of a structure 500 million light-years across, within which our galaxy is a single small member near the periphery. The map of where we are just became considerably more vertiginous. But here is what makes the Great Attractor truly strange, and what keeps it lodged in the category of genuinely impossible-feeling places rather than merely large but comprehensible ones. Even accounting for Laniakea and the mass of the Norma Cluster and all the surrounding superclusters, the observed velocities of the galaxies in this flow are still not fully explained. There are hints, contested, not yet confirmed, but persistent, that something even more massive lies beyond Laniakea, an even larger structure called the Shapley concentration, or Shapley supercluster, approximately 650 million light-years away, whose gravitational influence may extend across the entire region. And beyond even that, the full accounting of what is pulling what and by how much, and where the true gravitational center of our local cosmic neighborhood lies, remains an open and actively debated question in cosmology. The Great Attractor, in other words, is not a solved problem with a name attached to it. It is the name we gave to our awareness that something is pulling us toward a place we cannot fully see, within a structure whose total mass we cannot completely account for, in a direction that for decades we could not even observe directly. I want you to feel this for a moment. Really feel it, in whatever way is available to you as you lie here in the dark. The Earth is orbiting the Sun at roughly 107,000 kilometers per hour. The Sun is orbiting the center of the Milky Way at approximately 828,000 kilometers per hour. The Milky Way is falling toward the Great Attractor at approximately 2.2 million kilometers per hour. And all of this motion, all of this staggering multi-layered velocity through space, is happening right now, continuously, silently, without any sensation available to you because there is nothing to feel it against. The universe has no fixed reference point, no stationary background against which motion can be perceived as motion. You are hurtling through space at millions of kilometers per hour in several directions simultaneously, being pulled by a gravitational anomaly 200 million light-years away, embedded in a supercluster 500 million light-years across, and you feel completely, utterly still. That gap between the reality of our motion and the stillness we experience is one of the deepest strangeness I know of. The Great Attractor is pulling you. It has always been pulling you. You just had no way of knowing it until now. When the James Webb Space Telescope opened its golden eye for the first time in the summer of 2022, astronomers around the world were cautiously optimistic. They expected it to see farther than any telescope before it. They expected it to peer deeper into the early universe, to find galaxies at greater distances, to push the frontier of observation a little further back toward the beginning of time. What they did not fully expect, what, if we are being honest, the standard models of cosmology did not predict, was what Webb actually found in its first deep field images. Within weeks of the telescope beginning science operations, a cascade of papers began appearing, each one describing galaxies at redshifts higher than most astronomers had considered likely to be found. Each one describing objects that were not just distant but massive, not just old but structured, bright and chemically complex in ways that should have required billions of years of stellar evolution to produce. The early universe, according to everything we thought we understood about how galaxies form and grow, should have been populated by small, chaotic, dim proto-galaxies, the seeds of what would later become the majestic spirals and ellipticals we see in the nearby universe. What Webb found instead was something that sent a quiet tremor through the field of cosmology, and one galaxy, above the others, became the emblem of everything that was unexpected. GLASS Z13. The name comes from the survey that identified it, the GRISM Lens Amplified Survey from Space, which used the gravitational magnification of a foreground galaxy cluster to amplify and distort light from objects far behind it, effectively using the cluster as a natural cosmic telescope. GLASS Z13 was identified as a candidate high redshift galaxy in the first weeks of Webb science operations, and subsequently confirmed as one of the most distant galaxies ever observed. Its light left its source approximately 300 million years after the Big Bang, when the universe was roughly 2% of its current age. The light that carries its image to our telescopes has been travelling for approximately 13.5 billion years. It left its source before our Sun existed, before the interstellar cloud that would eventually form our solar system had even begun to condense, before the atoms that compose your body had been forged inside any star. This galaxy was already there, already luminous, already structured, already forming stars at a furious rate, in a universe that by our best models should barely have had time to form the first generation of stars at all. Here is the thing most people do not realize about galaxy formation. Galaxies do not appear instantly. They grow. They accumulate mass gradually through a process that involves the gravitational collapse of enormous clouds of gas, the ignition of star formation within those clouds, the gradual merging of smaller structures into larger ones over timescales of hundreds of millions to billions of years. The standard model of structure formation, called lambda CDM for lambda cold dark matter, makes specific predictions about how massive a galaxy can be at a given epoch in cosmic history, based on how much time has elapsed for material to accumulate and structures to grow. GLASS Z13 and a handful of similar galaxies discovered in Webb's early observations appear to be more massive, more luminous, and more structured than lambda CDM comfortably predicts for objects at their redshift. Not by a trivial margin, by factors that have caused cosmologists to use words like surprising and challenging, and, in some cases, in tension with our models. These are careful, measured words from careful, measured scientists. Translated into plain language, they mean, we did not expect this, and we are not entirely sure what it means. Let me try to make the strangeness of this concrete. Imagine you are an archaeologist and you are excavating a site that, according to your best dating methods, was occupied approximately 5,000 years ago. You expect to find simple tools, basic pottery, evidence of early agricultural practices. Instead, you find a printed circuit board, not a rough prototype, a sophisticated multi-layered printed circuit board of the kind that requires an advanced industrial civilization to produce. You know your dating is correct. You know the stratigraphy. The circuit board is genuinely 5,000 years old, but it should not exist. The civilization required to produce it did not exist at that time. Something in your model of history is wrong. Not wrong in a minor, adjustable way, but wrong in a way that requires serious rethinking of the timeline. Glass Z13 is that circuit board. It exists at a time when it should not be as massive or as structured as it is, and it is not alone. Webb has found multiple galaxies in this category. The anomaly is not a one-off, it appears to be a pattern. The scientific community is responding carefully and thoughtfully to these findings, as it should. Several explanations are being actively investigated. One possibility is that the stellar mass estimates for these early galaxies are being skewed upward by the presence of active galactic nuclei, black holes at their centres that are contributing luminosity and making the galaxies appear more massive than they actually are. Another possibility is that the efficiency of star formation in the early universe was significantly higher than current models assume, that the first galaxies converted their gas into stars at a rate that our simulations have underestimated. A third possibility, the most far-reaching and the most carefully considered among theorists, is that the standard cosmological model itself requires modification, that the initial conditions of the universe, or the properties of dark matter, or the physics of the early universe's expansion, are not quite what we have assumed them to be. None of these possibilities has been definitively confirmed. The field is in an active and genuinely exciting state of productive uncertainty, of the kind that tends to precede significant advances in understanding. But I want to stay for a moment with the raw strangeness of what Glass 13 represents before the explanations arrive and the strangeness gets smoothed over. There is a galaxy, real and confirmed, that formed when the universe was 300 million years old. 300 million years sounds like a long time in human terms. It is longer than the age of the dinosaurs, longer than the time since the Permian extinction, longer than almost any span of biological history on Earth. But in cosmological terms, 300 million years after the Big Bang is almost nothing. It is the first breath. It is the opening seconds of a 13.8 billion year story. And in those opening seconds, this galaxy had already assembled itself from the raw chaos of the early universe, ignited billions of stars, built structures and relationships between those stars, and begun radiating light that would travel for 13.5 billion years before arriving at a golden mirror in space and being recorded by instruments built by the descendants of those very stars. It should not be there, and yet there it is, faint and ancient and luminous, in the deepest images our finest telescope has ever taken, asking us quietly to think harder about what we thought we knew. We have arrived at the last of our 10 impossible places, and in some ways it is the strangest of all, not because of what it contains, but because of what it means. The other 9 places we have visited tonight are objects or regions or structures, things that exist somewhere specific, that have coordinates you could in principle point a telescope toward, that have properties that can be measured and debated and refined as our instruments improve. This final place is different. It is not a thing. It is a limit. It is the boundary of the knowable, the edge of the region of space from which light has had enough time, in the 13.8 billion years since the Big Bang, to travel to us. Beyond this boundary, the universe almost certainly continues. It may continue for an enormous distance. It may continue forever. But whatever lies beyond it is, in a very precise and permanent and deeply unsettling sense, invisible to us. Not invisible the way that something hidden behind an obstacle is invisible, waiting to be seen from a different angle. Invisible the way that the past is invisible, irretrievably, constitutively, beyond any possible act of observation, now or ever, regardless of how powerful our telescopes become or how long our civilization persists. The edge of the observable universe is the horizon of human knowledge, and standing at it, even in imagination, is one of the most vertiginous experiences the cosmos has to offer. Let me be precise about what this boundary is, because precision matters here, and the concept is easy to misunderstand. The observable universe has a radius of approximately 46.5 billion light-years. You might expect that number to be 13.8 billion light-years. The age of the universe in years times the speed of light, and the fact that it is larger requires a moment of explanation. Space itself is expanding. It has been expanding since the Big Bang, and the rate of that expansion means that objects which emitted light 13.8 billion years ago, when that light began its journey toward us, have since moved considerably farther away. The most distant light we can detect, the cosmic microwave background radiation, released approximately 380,000 years after the Big Bang, comes from regions that are now approximately 46.5 billion light-years away, even though they were only about 42 million light-years away when the light was emitted. The universe stretched the distance between us and those regions while the light was travelling. The observable universe is a sphere defined not by a physical wall, but by a temporal one. The look-back time of 13.8 billion years, combined with the expansion of space, produces a boundary 46.5 billion light-years in radius, beyond which no signal of any kind has had time to reach us. Now here is the part that I want you to sit with, because it goes further than most people realise. The expansion of the universe is not slowing down, it is accelerating. Driven by a mysterious repulsive energy that permeates all of space, what cosmologists call dark energy, a label that honestly means we've observed its effects and have very little idea what it actually is. The universe is expanding at an ever-increasing rate, and this acceleration has a consequence, that is, when you fully absorb it, one of the most terrifying facts in all of cosmology. There are galaxies that we can currently observe, galaxies whose light is reaching our telescopes right now, whose images we have photographed and catalogued and studied, that are already so far away and receding so quickly due to the expansion of space, that any light they emit today will never reach us. The expansion of space between us and them is already occurring faster than light can travel across it. Those galaxies are, in terms of any future communication or observation, already beyond our reach. We can see their past. We will never see their present, and as time goes on, more and more galaxies will cross this threshold, the cosmological event horizon, and disappear from our observable universe forever. The observable universe is not static. It is shrinking in the sense that matters most. The number of galaxies with which we can ever exchange information is decreasing, irreversibly, with every passing moment. In the very long run, on timescales of hundreds of billions to trillions of years, this process reaches a conclusion that is profoundly isolating to contemplate. Eventually, every galaxy outside our local group will have receded beyond the cosmological event horizon. The Milky Way and Andromeda will have long since merged into a single elliptical galaxy. The stars of that merged galaxy and the remnants of the local group will be all that remains visible. Every other galaxy in the universe, the hundreds of billions of galaxies currently catalogued in our deep field images, the structures and filaments and clusters and superclusters we have spent decades mapping, will have passed beyond the horizon of observation. A civilization of astronomers living in that distant future, looking out at the sky with instruments as powerful as they could build, would see nothing beyond their local group. No cosmic web, no evidence of the large-scale structure of the universe, no hint that hundreds of billions of other galaxies exist or ever existed. They would be as cosmically isolated as our pre-telescopic ancestors imagined themselves to be, and they would have no way of knowing otherwise. The universe will have hidden itself from them as completely and as permanently as if the rest of it had never been there. We are fortunate, in a way that I find genuinely moving, to live in the era we do. We exist at a moment when the universe is old enough to have produced stars and planets and life and curiosity, but young enough that the cosmic web is still visible, still spread across our sky in all its staggering complexity, still accessible to our telescopes, still available to be wondered at. 1 billion years from now, that window may be significantly narrower. 10 billion years from now, it may be effectively closed. The galaxies are already moving away from us faster than light in the regions beyond the cosmological event horizon, and the accelerating expansion means that horizon is encroaching inward, swallowing more and more of the observable universe into permanent invisibility. This is not a crisis on any human timescale. It will not affect anyone alive today, or anyone alive for billions of generations to come, but it is real. and knowing it is real changes something about the act of looking up at the night sky. It makes that act feel less like a passive observation and more like a privilege. The universe is showing us something right now, in this epoch, that it will one day stop showing. The cosmos, in its long and indifferent history, has briefly opened a window. We happen to be here while it is open, and that, I think, is worth pausing to notice. Everything we have visited tonight has been visible, in the broadest sense of that word. Not visible to the naked eye. Most of these places require radio telescopes, infrared observatories, X-ray satellites, or instruments operating at wavelengths the human eye was never designed to detect. But visible in the sense that they emit or absorb or deflect something we can measure. The Boötes void is visible by the absence of galaxies in a region where we expected to find them. Sagittarius A star is visible in radio waves and in the orbital motion of the stars that circle it. Stephenson 218 is visible in infrared light. TON 618 shines so brightly that its light crosses 10 billion light-years of expanding space and still registers in our detectors. Even the edge of the observable universe is visible, faintly, as a glow of microwave radiation filling the entire sky. Everything we have explored tonight has left some kind of trace, some detectable imprint on the instruments we have built to look. But the thing I want to tell you about now leaves almost none. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind that we have been able to detect, despite decades of searching with increasingly sensitive instruments, designed specifically to find it. And yet it makes up approximately 27% of everything that exists. It is the dominant form of matter in the universe, and without it, none of the 10 places we have visited tonight would exist at all. Dark matter is the most consequential thing we have never seen. The evidence for its existence is overwhelming, and comes from multiple independent lines of observation that have been accumulating since the 1930s, when the Swiss astronomer Fritz Zwicky first noticed that the galaxies in the Coma Cluster were moving far too fast to be held together by the gravity of their visible mass alone. If the only gravity available to the Coma Cluster came from the stars and gas that could be seen and measured, the cluster should have flown apart long ago. The galaxies were moving with velocities that far exceeded the escape velocity implied by the visible matter. Something else had to be providing additional gravitational mass, something invisible. Zwicky called it Dunkelmaterie, dark matter, and was largely ignored for decades. It was not until the 1970s, when astronomer Vera Rubin and her colleague Kent Ford studied the rotation curves of individual galaxies, that the reality of dark matter began to be taken seriously as a mainstream scientific proposition. Rubin found that stars at the outer edges of galaxies were orbiting at roughly the same speed as stars near the centre, a result that directly contradicted what Newtonian gravity predicts for a system where most of the mass is concentrated in the visible disk. The stars at the edges should be orbiting much more slowly, as the planets in the outer solar system orbit more slowly than those near the Sun. They were not. The only explanation that fit the data was that each galaxy was embedded in a vast invisible halo of additional mass, a halo of dark matter extending far beyond the visible galaxy and providing the extra gravitational pull needed to keep the outer stars in their orbits. This was not a minor correction. The dark matter halo of a typical galaxy is estimated to contain approximately 5 to 6 times the mass of all the visible stars and gas in that galaxy combined. At the scale of the cosmic web, the large-scale structure of filaments, walls, and voids that we briefly visited when we explored the Boötes void, dark matter is not merely a corrective footnote, it is the architect. The visible cosmic web, the threads of galaxies and clusters that span hundreds of millions of light-years and form the largest structures in the observable universe, is a tracer of an underlying dark matter web that formed first and pulled ordinary matter into its gravitational scaffolding. In the very early universe, fractions of a second after the Big Bang, tiny quantum fluctuations in the density of dark matter began to grow under their own gravity, forming an invisible skeleton of slightly denser and slightly less dense regions. Ordinary matter, the hydrogen and helium gas that filled the early universe, could not collapse on its own during this period because it was coupled to radiation and subject to pressure forces that prevented gravitational collapse. Dark matter, interacting only gravitationally, was immune to this pressure and could begin forming structure immediately. By the time ordinary matter decoupled from radiation 380,000 years after the Big Bang, the dark matter skeleton was already in place. The gas fell into the gravitational wells the dark matter had prepared for it, cooled, condensed, and eventually ignited into stars. Every galaxy in the observable universe formed inside a dark matter halo. Every filament of the cosmic web traces a dark matter filament beneath it. Every void, including the Boat's void, is a region where the dark matter density was low enough that matter flowed away rather than accumulating. The universe we can see is the shadow of a universe we cannot. The most sophisticated computer simulations of cosmic structure formation, programs that model the gravitational interactions of billions of particles representing dark matter across volumes of space hundreds of millions of light years across, reproduce the observed cosmic web with extraordinary fidelity when dark matter is included in the simulation, and fail dramatically when it is not. The filaments appear in the right places, the clusters form at the right intersections, the voids open up to the right scales. The statistical properties of the large-scale structure match the observations with a precision that leaves little room for doubt about the reality of dark matter as a gravitational influence. What the simulations cannot tell us, what decades of direct detection experiments in underground laboratories, particle colliders, and satellite observations have so far failed to reveal, is what dark matter actually is. We know what it does. We have mapped where it is, at least statistically, through a technique called gravitational lensing, the way dark matter bends light passing through it, producing detectable distortions in the images of background galaxies. We know its total quantity, we know its gravitational properties, we do not know its composition, we do not know what particle or particles it consists of. We have proposed candidates, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and we have searched for each of them with extraordinary care and found nothing definitive. The universe's dominant form of matter remains, after nearly a century of increasingly sophisticated inquiry, completely unidentified. I want to leave you with the full weight of that for a moment. When you look at an image of the cosmic web, the beautiful, filamentary, almost biological-looking structure of galaxy clusters connected by threads of luminous matter across hundreds of millions of light years, you're looking at approximately 5% of what is actually there. The ordinary matter that makes up stars, gas, planets, and everything you have ever touched or seen or known comprises roughly 5% of the total energy content of the universe. Dark matter adds another 27%. The remaining 68% is dark energy, the repulsive force driving the accelerating expansion of the universe, about which we know even less than we know about dark matter. The universe, in other words, is 95% composed of things we cannot identify, cannot directly detect, and do not understand in any fundamental sense. The 10 impossible places we have visited tonight, the void, the black holes, the hypergiant star, the cold spot, the quasar, the pulsar, the minimum star, the great attractor, the impossible galaxy, the edge of the observable cosmos, all of them exist inside a universe whose dominant components are almost entirely unknown to us. We are not exploring the universe, we are exploring 5% of it. And everything we have marvelled at tonight, every number that staggered us, every scale that defeated comprehension, is drawn from that thin, luminous, visible sliver. What the other 95% contains, we can only begin to imagine. We have been travelling for a while now. We have stood at the edge of a void 330 million light-years of almost nothing. We have looked into the shadow of a 4 million solar mass black hole at the centre of our own galaxy. We have tried to hold in our minds the radius of a star that would swallow every planet from Mercury to Saturn. We have examined a cold patch in the oldest light in the universe that may be the bruise left by a collision with another universe entirely. We have visited a quasar powered by a black hole 66 billion times the mass of the Sun. We have learned that time runs slower near a spinning dead star 500 light-years away. We have found a star barely larger than Saturn that is nonetheless burning with nuclear fire. We have felt the invisible pull of something enormous drawing hundreds of thousands of galaxies across hundreds of millions of light-years. We have looked at a galaxy that existed 300 million years after the Big Bang and should not have been as large or as structured as it was. And we have stood at the edge of the observable universe and contemplated the permanent invisibility of everything beyond it. We have, In other words, taken a fairly thorough inventory of how extreme the universe is willing to be, and at some point after enough of these extremes have accumulated, a different kind of question begins to form. Not what are these things, or how did they get this way, but why? Why does the universe allow any of this at all? The question sounds philosophical, and it is. But it is also, in a very real sense, a scientific question. One that sits at the boundary between cosmology and what philosophers call metaphysics, in the contested and fascinating territory where the two fields have to decide between themselves who gets to ask which questions. The universe we inhabit is governed by a set of physical laws and constants. Numbers like the gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force, the cosmological constant that governs the expansion of space. These numbers are not derived from any deeper theory. They are, as far as we can currently determine, simply the values they happen to be. And those values, collectively, determine everything about what the universe is capable of producing. Change them, even slightly, and the universe looks radically different. Change the strength of the strong nuclear force by a few %, and carbon cannot form in stellar interiors, eliminating the chemical foundation of all known life. Change the cosmological constant upward by a modest factor, and the universe expands so rapidly after the Big Bang that no structure ever forms. No galaxies, no stars, no planets, no voids, no quasars, no anything. Change it downward, and the universe collapses back on itself before stars have time to ignite. The constants that govern our universe sit, in case after case, in narrow ranges that permit the universe to be complex, structured, and inhabited. The question of why they sit in those ranges is one of the deepest unanswered questions in all of science. The extremes we have visited tonight are a direct consequence of these constants and the laws they define. Black holes exist because gravity, as encoded in the gravitational constant and in the equations of general relativity, behaves in a specific way at extreme densities. Stellar hypergiants exist because nuclear physics permits stars to accumulate mass up to a certain limit before radiation pressure tears them apart. Voids exist because the initial conditions of the universe, combined with the attractive nature of gravity and the repulsive influence of dark energy, cause matter to redistribute itself in a specific way over cosmic time. The minimum star exists because the strong nuclear force has the particular strength it does, setting the threshold for hydrogen fusion at precise mass. Every extreme place we have visited is, in this sense, a consequence, an inevitable output of the specific physical laws and constants that define our universe. The universe does not contain these extremes by accident. It contains them because its rules permit them. Because its rules, in every case, allow matter and energy and space-time to evolve until they reach these configurations. The universe generates extremes because it is built to generate them. This observation sits at the heart of what cosmologists and philosophers call the fine-tuning problem, and it pulls in two very different intellectual directions simultaneously. The first direction leads toward what is sometimes called the anthropic principle, the observation that the universe's constants must be compatible with the existence of observers, because if they were not, there would be no observers to notice them. In its weak form, this is simply a logical tautology. We find ourselves in a universe compatible with our existence because that is the only kind of universe we could find ourselves in. In its stronger forms, it becomes considerably more provocative, suggesting that the existence of observers may play some role, however indirect, in selecting or explaining the values of the constants. Most physicists are cautious about the stronger versions of the anthropic principle, and rightly so. But the weak version is inescapable, and it carries a strange kind of comfort. The extremes we have visited tonight, the very features of the universe that trigger vertigo and awe, and the quiet tremor of existential wonder, are part of the same physics that allows us to exist and notice them. The void and the observer are products of the same set of rules. The quasar and the curiosity that wanders about it emerge from the same underlying laws. The second direction leads toward the multiverse. If the constants of our universe are fine-tuned, if slight changes would produce a sterile, structureless, lifeless cosmos, then one possible explanation is that our universe is not the only one. In a sufficiently large ensemble of universes, each with different values of the fundamental constants, some small fraction would by chance have constants compatible with complexity, structure, and life. We find ourselves in one of those universes not because it was designed for us, but because it is the only kind in which we could exist. This idea, sometimes called the anthropic multiverse, is controversial, not because it is obviously wrong, but because it is extraordinarily difficult to test. A universe with different physical constants is, almost by definition, not accessible to observation from within our universe. But the framework of eternal inflation, which we touched on briefly when discussing the CMB cold spot, does predict the existence of a vast ensemble of bubble universes with varying physical properties, providing at least a theoretical mechanism by which such an ensemble could arise. The evidence is indirect, the debate is genuine, and the question remains open in the most honest and productive sense of that phrase. What I want to offer you, as we move through the final chapters of tonight's journey, is not a conclusion to this question, but a way of holding it. The universe is extreme. It contains voids and hypergiants, and ultra-massive black holes and minimum stars and impossible early galaxies, and the permanent darkness beyond the observable horizon. It also contains you, a temporary, fragile, cosmically insignificant arrangement of atoms that has somehow developed the capacity to contemplate all of these things, to feel something in response to them, to ask why they exist and what they mean. The extremes and the wonder they produce are not intention. They are, I think, the same thing. The universe built something capable of being astonished by itself, and that astonishment, quiet, sustained, nocturnal, the kind you feel lying in the dark thinking about things that are too large to think about, is perhaps the most extreme thing the universe has managed to produce. There is a temptation, when you spend time thinking about the universe, to focus exclusively on what is there. The stars, the galaxies, the black holes, the filaments of the cosmic web, glowing with the light of billions of suns. These are the things that announce themselves, that demand attention, that give the universe its drama and its scale and its beauty. We are drawn to presence, we are drawn to light. It is perhaps the deepest habit of a species that evolved to navigate a world by seeing it, that built its civilizations around fire and the sun and the illuminated page. But the universe is not primarily made of presence. It is primarily made of absence. When cosmologists map the large-scale structure of the observable universe, what they find, on the largest scales, is that the luminous matter, the galaxies and clusters and filaments that contain all the stars that have ever shone, occupies only a small fraction of the total volume. The rest is void, empty, dark, expanding regions of space where the density of matter has fallen below any threshold that would permit stars to form or galaxies to congregate. The voids are not the background against which the universe happens. They are half the story, perhaps more than half. And they have been trying to tell us something that, if we listen carefully enough, changes the way the whole picture looks. We began tonight in the Bhuta's Void, the largest single void in the observable universe, 330 million light-years of almost nothing, containing roughly 60 galaxies where 2,000 might be expected. We described it as empty, as anomalous, as a region where the cosmic web simply does not exist. All of that is true, but I want to return to it now from a different angle, because there is something about the Bhuta's Void and voids in general that gets overlooked when we frame them purely in terms of absence. Voids are not random. They are not scattered arbitrarily across the universe like holes punched through a fabric by some blind and structureless process. They are instead precisely located, bounded by the filaments and walls and clusters that form the cosmic web, fitting between those structures the way the spaces between the threads of a net fit between the threads. The voids and the filaments are two aspects of a single, coherent, large-scale structure. They are defined by each other. You cannot have the cosmic web without the voids, any more than you can have the threads of a net without the holes between them. The voids are structural. They are load-bearing, in a gravitational sense, because the boundaries between voids and filaments are precisely where the flows of matter converge, where dark matter halos grow, where gas cools and condenses, where galaxies form and cluster and evolve. The emptiness is not where nothing happened. It is where matter decided to go somewhere else, and the somewhere else it went is where everything we find most interesting ended up. The cosmic microwave background cold spot, the second void-like structure we explored tonight, adds a different dimension to this story. Unlike the Bhuta's Void, which is a feature of the present-day universe, a structure that has grown and deepened over billions of years of gravitational evolution, The cold spot is potentially a feature of the early universe, imprinted on the cosmic microwave background at a time when the universe was only a few 100,000 years old and the large-scale structure we see today had barely begun to form. If the cold spot is indeed caused by a supervoid, an enormous underdensity in the distribution of matter along the line of sight toward the southern sky, then it represents a void so large and so deep that it leaves a detectable imprint not just on the distribution of galaxies, but on the oldest light in the universe itself. It reaches back through cosmic history and marks the background radiation the way a thumbprint marks a piece of clay. The void is not just a present-day feature, it is a presence embedded in the memory of the universe, recorded in the afterglow of the Big Bang, persisting as a cold and slightly anomalous patch in a map of the sky that otherwise encodes the initial conditions from which all of cosmic history unfolded. Now step back even further, to the scale of the entire observable universe, and look at what the voids collectively reveal. One of the most powerful tools in modern cosmology is the statistical analysis of the distribution and sizes of voids in large galaxy surveys. The way voids are distributed in space, how large they tend to be, how deep, how numerous, how they cluster and border each other, is exquisitely sensitive to the properties of dark energy, the mysterious repulsive force driving the accelerating expansion of the universe. In a universe with different dark energy properties, the voids would be different. They would be distributed differently, sized differently, emptied at different rates. By measuring the actual voids in our universe with precision surveys like the Sloan Digital Sky Survey and its successors, cosmologists can constrain the properties of dark energy in ways that complement measurements from supernova and the cosmic microwave background. The voids are not just empty space, they are in this sense precision instruments, natural laboratories for measuring the invisible force that is reshaping the universe on its larger scales. The silence between the filaments is telling us something about the engine of cosmic expansion that we cannot easily read from the filaments themselves. And here is what I find most remarkable about all of this, and what I want you to carry with you into the final chapters of tonight's journey. The pattern of the cosmic web, filaments, walls, clusters, and voids distributed across hundreds of millions of light-years in a structure that looks, in two-dimensional projection, startlingly similar to the network of neurons in the human brain, or the distribution of blood vessels in living tissue, or the structure of certain kinds of foam. This pattern is not a coincidence or an aesthetic curiosity. It is the direct output of the initial conditions of the universe, processed through 13.8 billion years of gravitational physics. The quantum fluctuations that seeded the structure were present in the first fraction of a second after the Big Bang, stretched to cosmic scales by inflation, imprinted on the cosmic microwave background, and then amplified by gravity over the entire subsequent history of the universe into the web we observe today. The voids are where they are, because of events that occurred in the first microseconds of existence. The Butter's void, the cold spot, the vast empty cells of the cosmic web. All of them are the echoes of quantum noise from the birth of the universe, grown large over billions of years into structures that span hundreds of millions of light-years of space. The largest features of the observable universe are the grown-up children of the smallest possible fluctuations. The silence has always been there. It was there before the first star ignited, before the first galaxy coalesced, before any light existed to illuminate the filaments between the voids. In the beginning, there was something very close to nothing, a nearly uniform, nearly featureless, almost silent expanse of energy. And from that near silence, through the patient amplification of the tiniest possible differences, everything that exists was eventually assembled. The voids remember that origin. They are the parts of the universe that have changed the least. They are the closest thing to the beginning that we can still visit. Nothing we have visited tonight is permanent. This may seem like an obvious thing to say. Nothing in the universe is permanent. Everything changes. Everything evolves. The second law of thermodynamics sees to that with a patience and a thoroughness that nothing in the cosmos has ever successfully defied. But I want to say it specifically about the 10 impossible places we have explored, because the timescales of their futures are themselves extraordinary, because the way these places will change, and the things they will become, extend the story of the universe so far beyond the present moment that our current epoch, with all its stars and galaxies and complexity and life, begins to look like the briefest of opening acts in a drama whose later chapters are almost incomprehensibly strange. The universe has a future. It is a long one, and in that future, every place we've visited tonight will be transformed beyond recognition. Let me take you there, slowly, one step at a time, into the deep future of a cosmos that is only just beginning. The stars will go first, not immediately. The universe is currently in what astronomers call the stelliferous era, the age of stars, which began shortly after the Big Bang and will continue for approximately 100 trillion years into the future. 100 trillion years. Our universe is currently 13.8 billion years old, which means the stelliferous era is less than 0.1% complete. There are stars being born right now, in molecular clouds across the Milky Way, and in galaxies throughout the observable universe, that will still be burning long after the sun has exhausted its fuel, collapsed to a white dwarf, and faded to a cold dark cinder. The smallest red dwarf stars, objects not unlike EBLM J0555-57ab, the minimum star we visited earlier tonight, burn so slowly and so efficiently that they will continue fusing hydrogen for trillions of years, outlasting every star of the sun's size or larger by factors of hundreds. But even they will eventually exhaust their fuel. Even the most patient, most frugal, most long-lived stars in the universe will one day stop burning. The stelliferous era will end, the last star will fade, and the universe will enter a darkness that has no analogue in the cosmos we currently inhabit. A darkness not just of the night sky, but of everything, everywhere, with no new light to replace what has been lost. What happens to our impossible places in this stellar twilight and beyond? The Bhuta's void will continue to grow. Dark energy, accelerating the expansion of space, pushes matter increasingly toward the filaments and clusters that bound the void, deepening the emptiness at the void's center, while the structure at its edges thickens and contracts. Over hundreds of billions of years, the cosmic web will continue to evolve in this direction. Filaments merging into walls, walls contracting into clusters, clusters falling into superclusters, while the voids between them grow ever larger and ever emptier. Eventually, in the very far future, the structure of the universe will consist of isolated islands of gravitationally bound matter, remnants of merged galaxy clusters, surrounded by voids of ever-increasing size as the expansion of space carries everything else permanently out of reach. The Bhuta's void of today is a preview of what most of the universe's volume will look like in the far future: empty, dark, cold, and growing. Sagittarius A star will outlast the stars that currently orbit it. Black holes, unlike stars, do not burn through fuel in any conventional sense. They grow by consuming matter, and they shrink, extraordinarily slowly, through a quantum mechanical process called Hawking radiation, by which they emit a faint trickle of thermal radiation and gradually lose mass. For a black hole of Sagittarius A star's mass, 4 million solar masses, the timescale for complete evaporation via Hawking radiation is approximately 2 × 10⁻83 years. That number is so large it requires a moment of honest acknowledgement. It is vastly longer than the current age of the universe, longer than the stelliferous era, longer than almost any timescale that arises naturally in cosmology. For all practical purposes, Sagittarius A star is functionally eternal by human standards, but not by the standards of the deep future. Given enough time, and the universe, it appears, has enough time, even a 4 million solar mass black hole will eventually evaporate completely, releasing its mass as a final burst of Hawking radiation and leaving behind nothing. No singularity, no event horizon, nothing. The sleeping monster at the heart of our galaxy will, in the end, simply cease to exist. TON 618, with its 66 billion solar masses, will take proportionally longer, an almost absurdly longer time, but it too will eventually evaporate. Every black hole in the universe will eventually evaporate. The universe, given enough time, erases even its most extreme objects. Stephenson 218 will not survive anywhere near as long as the black holes. Red hypergiants like Stephenson 218 are, as we discussed, stars in the late stages of their lives, objects burning through their fuel at rates that are spectacular, precisely because they are unsustainable. Stephenson 218's future likely involves one of 2 dramatic endpoints. It may shed its outer layers in a series of violent pulsations, gradually losing mass until its core can no longer sustain the expansive phase that makes it a hypergiant, contracting into something smaller and hotter before eventually exploding as a supernova. Alternatively, it may collapse more directly, its core imploding on timescales of seconds in a core collapse supernova that, for a brief moment, releases more energy than the Sun will emit over its entire 10 billion year lifetime. Either way, the star that today spans the orbital distance of Saturn will be gone, transformed into either a neutron star or a black hole surrounded by an expanding nebula of expelled stellar material. The largest visible object we have visited tonight is also, in cosmic terms, one of the most temporary. And what of the observable universe's edge, that final boundary beyond which nothing can reach us? It will continue its slow encroachment. As dark energy accelerates the expansion of space, the cosmological event horizon, the boundary beyond which signals can never reach us, will pull inward over time, swallowing more and more of the currently observable universe into permanent invisibility. Galaxies that we can see today will recede beyond the horizon. Their light, already ancient by the time it reaches us, will redshift toward invisibility, their signals weakening and stretching until they can no longer be detected by any instrument. The observable universe will not literally shrink. The light that has already reached us carries information about the distant past, and that information is preserved. But the universe we can actively observe in real time, the universe from which we can receive new information, will contract around us as expansion accelerates. Eventually, in the far future, the night sky of whatever observers exist will be nearly dark, the merged remnant of the local group surrounded by an infinite and invisible expanse of receding, inaccessible space. The universe will have grown so large and its content so dispersed that it will resemble, in its own way, the Buddha's void. Emptiness in every direction, dark and cold and vast, with the last remnants of structure clustered in a small island of gravitationally bound matter adrift in an ocean of expanding nothing. The universe that began in heat and light and extraordinary density will end, after an almost incomprehensible duration, in cold and dark and silence. Not a dramatic ending, not an explosion or a collapse, just a slow, patient thermodynamic unwinding, the universe spreading itself thinner and cooler and quieter, until even the concept of change becomes meaningless, and time itself has nothing left to measure. We have travelled a long way tonight, together, in the dark, in the quiet, in whatever space you have made for yourself to lie still and let the cosmos in. We have gone to places that the human mind was not built to hold, and held them anyway. We visited a void 330 million light-years across, so empty it should not exist. We stood at the threshold of a 4 million solar mass black hole, 26,000 light-years from the bed you're lying in right now. We tried to feel the radius of a star that would swallow Saturn's orbit. We examined a cold patch in the oldest light in the universe that may be the fingerprint of another universe entirely. We looked into the heart of a quasar powered by 66 billion solar masses, burning with a light that outshines entire galaxies. We learned that time runs slower near a spinning dead star and faster where you are. We found a star barely larger than Saturn that is nonetheless a sun. We felt the invisible pull of something enormous drawing everything in our cosmic neighbourhood toward a point we spent decades unable to see. We found a galaxy in the deep past that should not have been as large as it was. And we stood at the edge of the observable universe and contemplated the permanent, irreversible darkness beyond it. 10 places. 10 moments of honest, quiet vertigo. And now we are here, at the end, and I want to say something about what all of it means. Not scientifically, not cosmologically, something more personal than that. You are made of star stuff. This is a phrase that has been said so many times it has almost lost its power, and I want to give it back some of that power tonight, because it is not a metaphor or a poetic flourish. It is a literal, precise, physical description of your origin. The carbon in your body was forged in the cores of stars that lived and died before our sun was born. The oxygen you breathe was produced in supernovae, the violent deaths of massive stars, events of the same category that await Stephenson 218 at the end of its brief and blazing life. The iron in your blood was created in the final moments of stellar collapse, in the most energetic explosions the universe produces outside of the Big Bang itself. Every atom in your body heavier than hydrogen and helium was manufactured inside a star, ejected into interstellar space, dispersed across light years of gas and dust, and eventually gathered by gravity into the molecular cloud that collapsed to form our solar system 4.6 billion years ago. You are not just living in the universe, you are assembled from it. You are the universe, in a very real and non-metaphorical sense, temporarily organized into a form that can breathe and think and feel and wonder. And here is what strikes me as the most extraordinary thing about that. The thing I want to leave you with as you drift towards sleep tonight. Of all the configurations the universe has produced, the voids, the hypergiants, the ultramassive black holes, the quasars, the minimum stars, the supervoids, the cosmic web, the galaxies that should not exist. Of all the extraordinary things the laws of physics have generated across 13.8 billion years of evolution, this configuration is the one that looks back. You're a temporary arrangement of stellar ash that has developed the capacity to be astonished by its own origin. The universe spent 13.8 billion years building the conditions necessary to produce something capable of noticing how strange and vast and improbable it is. And what it produced in the end was not something armoured against that strangeness, not something indifferent to the scale or the silence or the terrifying emptiness of the Bhuta's void. It produced something that feels it, something that lies in the dark and thinks about black holes and gets a little dizzy. Something that hears the phrase 330 million light years of almost nothing and feels a chill that has nothing to do with the temperature of the room. The universe, in producing you, produced its own capacity for awe. And awe, I think, is the most improbable thing the cosmos has ever made. I have been thinking as we have travelled together tonight about what it means to find a place impossible. None of the 10 places we visited are actually impossible. They exist. They have been measured. They obey the laws of physics even when they strain those laws to their limits or expose gaps in our understanding of them. What makes them feel impossible is the distance between their scale and ours, the gap between what the universe is capable of and what the human nervous system was designed to process. We evolved to navigate a world of human dimensions, distances measured in steps and days of walking, temperatures survivable by a body without fur or fire, timescales bounded by a single human life. The universe operates at dimensions that exceed every one of those scales by factors so large that our words for large numbers begin to feel inadequate. Billion, trillion, 10 to the power of 83. These are not really numbers, in the sense that 3 or 7 or 42 are numbers. They are gestures toward quantities that exceed the capacity of human intuition. And yet somehow, we gesture toward them anyway. We build the instruments, we do the mathematics, we write the papers and read them, and lie awake at night thinking about what they mean. We refuse, with a stubbornness that I find genuinely moving, to be bounded by the limits of our intuition. We insist on knowing things we were not built to know. That insistence, that refusal to stay within the comfortable boundaries of the perceivable, is perhaps the most distinctly human thing there is. And it is also, I think, the universe's way of understanding itself. The next time you look up at the night sky, tonight, tomorrow, next week, whenever the clouds part and the darkness is deep enough to see, I want you to remember something. The light reaching your eyes from those stars is ancient. Some of it left its source thousands of years ago. Some of it, from the faint smudges that are actually galaxies, left millions or billions of years ago. You are not looking at the sky. You are looking at the past, at a record of what the universe was, preserved in light that has been travelling toward you for longer than human civilization has existed. And somewhere out there, beyond what you can see, beyond the threshold of any telescope we have ever built or will build, the Bhuta's void is expanding. Sagittarius A star is waiting. Stevenson 218 is swollen and luminous and temporary. Ton 618 is burning with a light that outshines entire galaxies. The Great Attractor is pulling everything toward it at 2.2 million kilometers per hour, including you, right now, as you lie still. The universe is not static. It is not quiet. It is extraordinary and violent and ancient and strange beyond anything we have yet discovered. And you, made of its oldest materials, assembled by its most patient processes, are a small and temporary and genuinely remarkable part of it. Thank you for joining me tonight. Thank you for staying with me through all of it. The voids and the black holes and the dying stars and the edges of the knowable. If this journey meant something to you, If it gave you that particular feeling of smallness that is also wonder, I would be so grateful if you took a moment to like this video or subscribe to the channel. It is a small thing, but it helps more curious minds find their way here. And I can think of no better company for these nocturnal voyages than people who are willing to lie in the dark and think about the cosmos until it makes them a little dizzy. We are the universe noticing itself. We are stellar ash that learn to wonder, and that, of all the impossible things we have encountered tonight, is the one I find most beautiful. Sleep well. And the next time you find yourself outside under a clear and open sky, take a moment to look up at the stars. Really look. They are not just lights. They are your past, your origin, your distant and blazing family. And they have been waiting for billions of years for something made of their own material to look back and finally see them. Good night.